In this movie, we're going to talk about the basic actions of endocannabinoids, the natural analogs of the active ingredient in marijuana. Marijuana is the most popular recreational drug. The active ingredient in marijuana is tetrahydrocannabinol, abbreviated THC. The THC you inhale when you're smoking weed is what makes you high. I can't tell you exactly why THC gives you the munchies, but I will tell you how THC works in the brain. There are at least two natural cannabinoids, anandamine and 2-arachidiniol glycerol. Both substances will be referred to simply as endocannabinoids, the prefix endo referring to naturally produced cannabinoids. The endocannabinoids will be represented by the purple figure shown here. The receptors in the brain that bind the endocannabinoids are called Cb1 receptors, the Cb standing for cannabinoid. There's one of them right there. The Cb1 receptors are metabotropic receptors located in the presynaptic axon terminal. They don't occur on the postsynaptic cell, only on the presynaptic terminal. And Cb1 receptors are found throughout the brain and are one of the most abundant metabotropic receptors in the entire nervous system. They're found in the cortex. They're found in the hypothalamus, which of course might be what underlies the munchies. They're found in the hippocampus. They're found in the cerebellum and a whole variety of other places as well. But where do the endocannabinoids come from? And now comes the real surprise. Because they are synthesized in the postsynaptic cell from components of the cell membrane. The synthesis, indeed, is triggered by our old friend calcium. And what calcium does is it activates enzymes that synthesize endocannabinoids from lipid precursors in the cell's membrane. When there's calcium, it activates a series of events that I'm not going to describe, but the ultimate effect is to synthesize the endocannabinoids from the precursors in the lipid membrane. Here is the basic operation and effect of endocannabinoid signaling. First, the action potential invades the axon terminal, causing the influx of calcium, which in turn causes the release of transmitter from vesicles. The transmitter then binds onto the postsynaptic receptors and opens channels, allowing for the influx of positive charges that depolarize the cell. The depolarization then opens voltage-gated calcium channels in the postsynaptic cell. The influx of calcium, in turn, triggers the synthesis of endocannabinoids from membrane precursors. Now comes another surprise. Because the endocannabinoids are lipids, they can diffuse through the membrane of the postsynaptic cell and then bind onto the Cb1 receptors on the axon terminal. The activated G protein on the receptor then dissociates the beta-gamma complex, which binds to a voltage-gated calcium channel, causing the channel to close. While the cannabinoid is bound to the Cb1 receptor, the calcium channel cannot open, even when another action potential invades the terminal. The information flow is retrograde. After being synthesized in the postsynaptic cell, the endocannabinoid diffuses out of the postsynaptic cell and onto the receptor in the presynaptic cell, where it exerts its effects. The retrograde suppression of presynaptic transmitter release represents a mechanism by which neurons can communicate backwards across synapses to modulate their own inputs and thereby adjust synaptic strength. This retrograde suppression provides a way for the cell to use its own rate of firing to dynamically adjust the weight of the synapses that it receives. To illustrate the suppressive effect on a synapse, consider the same cell that was just illustrated, one in which the activity had generated an endocannabinoid response that closed the calcium channel on the presynaptic terminal. That response is shown here as the response to the previous action potential. Now imagine another action potential is generated in the presynaptic axon. The strength of the synapse now is diminished or suppressed due to the closure of a calcium channel on the terminal, and hence this action potential will evoke a weaker response in the postsynaptic cell than did the previous action potential. Perhaps you are wondering why the depolarization-induced calcium influx did not trigger long-term potentiation. The answer is that long-term potentiation requires the activation of calcium calmodulin activated kinase 2, or CAM kinase 2. But both calmodulin and CAM kinase 2 are localized in the postsynaptic density, just beneath the synaptic region of the postsynaptic cell, the region where NMDA receptors are located. Although it was not mentioned in previous lectures, voltage-sensitive calcium channels are present in the dendrites and soma of almost all neurons, but they occur at extrasynaptic sites that are removed from the synapse. Hence, when the postsynaptic cell is depolarized, what happens is that the depolarization opens the voltage-sensitive calcium channels, but the calcium entry does not activate the CAM kinase 2 because the CAM kinase 2 is localized at the synapse and thus distant from the calcium entering through the voltage-gated calcium channels. Rather, the enhanced calcium influx from voltage-gated calcium channels triggers the production of the fat-soluble endocannabinoids. So we have now seen how endocannabinoids are generated in the postsynaptic cell, how they work by retrograde signaling by diffusing out of the postsynaptic cell backward to the presynaptic terminal, and how they suppress transmitter release by closing voltage-gated calcium channels. The next movie shows how these features were demonstrated in inhibitory cells. We then will see how the suppression of inhibition in a simple network can enhance the effects of excitatory innervation in a postsynaptic cell and even facilitate the production of long-term potentiation.